So I've been working at IRIS-HEP for like 2 times basically on 2 projects. The first one was with Graham, where we actually have beaten C++ in jet reconstruction with Julia, but he's going to talk about that tomorrow. Today, I'm going to talk about Julia for AGC, which stands for Analysis Grand Challenge. So Analysis Grand Challenge is essentially about columnar data extraction and then processing of that data with different cuts into histograms. Right, we also apply some systematic uncertainties, and that also involves statistical models and visualizations in the end. The whole pipeline looks like this, and this is, I think it's not even the latest version of it, because the versions are coming out quite frequently, or at least they've been for a couple of months. This is probably for the version 1.2, where the machine learning inference has been added. We did not implement the machine learning inference because it was not our primary goal, but the whole pipeline, except for that thing, is kind of implemented. Right. Yeah, you can find more in the documentation. It's quite well documented. The data that was publicly available and basically available for us is quite big, as you can see. Each file is like about 3 gigabytes, and the smallest one is like 1 gigabyte, I think. So the AGC people wanted to have as many implementations as possible. So why not do that in Julia if we want to adopt Julia for high energy physics later on? So the main loop in Julia, which you can see on the right, you can probably see nothing here, but it's just for like to see the scale. It takes less than 100. In fact, it's about 80 lines of code here. And that includes the comments and gaps and really stuff that could have been a 1 line. So it's quite short. This is not the whole code, of course. This is not the whole project. But the entire project includes plotting, distributed versions for the main looper, and working with quite a lot of nested structures. Essentially, everything is like a nested dictionary of dictionaries and stuff like that. Right. So Julia, of course, is perfect for that. There was no problem working with that at all, and you all know that. The only problem that occurred was, in fact, related to the unroot and the fact that there was a bug that prevented us from reading from the URL. So if there was a root file, if there was like a remote root file, unroot pretended to read it and then just broke somewhere in the middle, which is already fixed, by the way. So that was the only like really unfixable issue, which is already fixed. Now, if we compare like the COFIA, which is our reference implementation, by the way, is in COFIA, and the pipeline that I showed was like from the AGC people. This is mainly what they work on, and this is the COFIA one. It's basically in Python, and it has kind of the object-oriented style here, which is a matter of preference, of course, but it's obviously not a way to do that in Julia. Right, so they have this processor abstract class, which is kind of the thing that you need to inherit from, and then you define all these different methods, and the main loop goes there in the process function. For us, it's several different get histo functions. Basically, they all do different stuff. The first one is kind of like the general wrapper of everything that you might need, which you can call with 0 arguments, and it will still work. And then everything else is like the more detailed versions. Yeah, there's also some dispatch used here. Right, and the main loop goes there. So that code that I showed with like 80 lines of code, it's here. If you're interested in which cuts do we make for the histograms, for AGC in general, it's basically that we count. So for each event, we only take events that have more than 4 jets, like 4 or more jets, with the PT that is more or equal to actually more than 25. In the reference implementation, there was actually a bug where they had more equal here, and it produced results not as expected. And then for that event, we count the B tags, and if the number of B tags that are higher or equal to 1 is higher or equal to 2, we add that event to the mass histogram. The mass is computed with some combinatorics, which are implemented like extremely differently from the reference implementation, I need to say. And otherwise, it's added to the HT histogram, which is the easier thing to do. Our main features, as I've already mentioned, that includes pipeline, like the entire pipeline without the ML-related parts. Also, we are obviously generating correct histograms with like correct data. The only thing that differs us from the reference implementation are bin migrations, which are kind of unfightable between different implementations. So that means that there are some events that just migrate between neighboring bins. And yeah, we've implemented systematics, which, I mean, there's quite a lot of different ways to do that. And the way we chose was the straightforward one, which is basically, so here you can see the, I have the all hists object, which is basically a dictionary of dictionaries that you index with symbols. We only take the events that are TT-bar events from there. And then we receive this huge dictionary of, once again, symbols to histograms. Now, each name of that symbol kind of represents what histogram that is, which systematic variation that is, and yeah, whether the systematic is like up or down. For some of them, we only save the up version if the down can be reconstructed from the up symmetrically. Yeah, I need to mention that I'm not that bad at naming, and those names are kind of enforced by the reference implementation to some extent. So like, it's not something I made up. Yeah, it's not that long because of me. Right, it has some pattern to it, so it's quite easy to get like to come up with the name that you need if you need some sort of a histogram there, but. Anyways, this is the way we did histogram. We did the systematic variations. Right. I also can show you the scaling of the distributed version of the project, which I mean, it's up to you to judge how that works out. We did that on like at U Chicago with the 25 physical nodes. So I'm well, again, up to you to judge. I'm not sure what I'm like. I need to show you some sort of a data about distributed computing, right? So this is the only thing that we have in that regard. And we also implemented the needed and like visualization tools that were implemented in the reference implementation, which is a pretty common thing. I think I only showed 2, but there are like 3 or 4 of the most common charts that one needs to construct with that yeah, with that tool. We've made that in Julia. It was obviously quite easy. I think we used make Maki or something like that. The whole workspace can be exported into a single JSON file compatible with cabinetry and PyHF, and that might sound like a quite a short thing, and well, quite a minor tool, but in fact, the code for that takes more than the main loop, because the format that cabinetry expects is kind of reversed to what we have. So the in many cases, the keys and values are swapped. In many cases, it's just different names for different stuff. So you need to have like also just code up the ways of renaming. If you have, say, a certain histograms, it's the name of those systematic variations are different in cabinetry than for us or the reference implementation. So it's basically a huge expression that just has a dictionary. It's basically a huge dictionary expression, like, I don't know, 100 lines of code. And we create the dictionary and then we just write it into a JSON file with a single line. Yeah. So this is it's not like, it's relatively straightforward how one approaches that thing, but it still took time and code to write that because it's really a lot of nested generators and stuff. The good thing is that we found some issues in the reference implementation that, of course, we just did not accept to our implementation. We just fixed them directly. But the reference implementation contained, I think, two major bugs. One is in that workspace like export to the JSON file. I mean, it's easy to make a mistake there. So they just did a typo kind of. And then the other thing is the one that I've mentioned, that it actually produced the results that they do not expect to produce because of like a single more than or equal sign. So the further steps for this thing include we need to release it yet. It's not like it doesn't have any release, but to do that, we need to implement more tests because the tests are not that good for now. They don't really. Well, the problem with test was that the files are like too big to actually try to do that. But then, I mean, to download them, like to put them in the repo, it's just impossible. But then, if we were to do that remotely, we need unroot to have access to the remote files, which it did not have up until recently. Right, so we need to do more tests, and we need to polish the repo and move it to the Julia-HEP maybe, because that seems like a nice thing that we did. Right, I think that's it. Thank you.